Alright everyone, today in this lesson we are going to be working with our complex roots some more, but we're also now really going to be working backwards from what we did before. So now this lesson we'll be starting with the factors and figure out what is the equation that created these factors, and for the most part we're going to be working with the compound root factors. So before we get started, we're going to take a look at a little bit of review. It says find the roots of each of the following quadratic functions by solving for x when y equals 0. So anytime you solve for the roots, remember you do set the y equal to 0, and then I'm just solving for x. So this is an undoing, so I'm going to subtract 9 and get x plus 5 quantity squared equals -9. I'd have to take the square root of both sides, and I'd have x plus 5 equals plus or minus the square root of 9, which gives me x plus 5 equals 3i, plus or minus 3i, and I subtract 5. So my final answer would be x equals -5 plus or minus 3i. So notice the real number, there's going to be two answers there. It's really -5 plus 3i and then -5 minus 3i. So we get two answers. The real number is always -5, but the imaginary part is opposite. If we look at the same thing here, now this isn't going to be in standard form, so you could either do completing the square, you could also do the quadratic form, whatever you prefer. I'm going to complete the square. So again, I'm saying the y equal to 0, and then I'm going to take half my middle term, so -2, square that, and then square that number. That's what we're missing. So 2 squared is 4. I'm missing 4, but I had 9. And when I add those like terms at the end, it would be plus 5. And now I start undoing. So I'm going to subtract 5 and get x minus 2 quantity squared equals -5. Square root both sides. You get x minus 2 equals plus or minus I root 5. I add my 2 to it, and so my final answer is x equals 2 plus or minus I root 5. So again, notice there's really two answers, 2 plus I root 5, 2 minus I root 5. The real number part is the same for both of them, the 2, and then the imaginary part is opposite because I have a positive I root 5 and then a negative I root 5. As we go on to 83, it's telling you to look for patterns as you calculate the sum and the product. So again, sum means you're going to be adding. So in this case, for letter A, I'd be doing 2 plus I plus 2 minus I. So 2 plus 2 is 4. I minus I is just 0. So the sum would be 4. And then my product, I'm going to have to FOIL that. So 2 times 2 is 4. 2 times -I is -2i. I times 2 is positive 2i. And I times -I is -I squared. The i's cancel out there. And notice I'd have 4 minus a -I. 4 minus I squared is -1. So that double negative makes it positive. So the product would be 5 for letter A. For letter B, the sum would be 3 minus 5i plus 3 plus 5i. So again, 3 plus 3 is 6, and your imaginary numbers cancel out there. The product, again, I'm going to have to FOIL that. So I'd be having 3 times 3 is 9. 3 times positive 5i is positive 15i. Negative 5i times 3 is -15i, and then negative 5i plus 5i is -25i squared. So notice those i's cancel there, and I'd be having 9 minus 25 times -1, and so that becomes 9 plus 25, or 34. So again, it becomes a real number there. I'm going to do C down here. So C, my sum it'd be negative 4 plus I plus a negative 4 minus I. So I would have negative 4 minus 4 more is negative 8, and your i's cancel out. So I get negative 8. For my product, I'd have negative 4 plus I, negative 4 minus I. And again, I'm foiling that, so that would be 16 plus 4I minus 4I and minus I squared. Your i's are going to cancel there, and then my I squared is negative 1. So it's 16 minus a negative 1, which becomes 17. So again, another real number. For letter D, the sum, I would have 1 plus 1 is 2. And then my I root 3 minus I root 3, they cancel out. So I'm left with just 2. My product, that gets a little trickier. I'll write that out. So it'll be 1 plus I root 3, 1 minus I root 3. And I FOIL. So 1 times 1 is 1. 1 times negative I root 3 is negative I root 3. I root 3 times 1 is positive I root 3. And then my last would be negative. Positive times a negative is negative. I times I is I squared. And then root 3 times root 3 is just 3. All right, so those I root 3, negative I root 3, positive I root 3 cancels, and I'd have 1 minus negative 1 times 3. So that really would be 1 plus 3 or 4. So another real number out of that. So if you notice, we had complex numbers to start for all of these, and we ended up with real numbers when we took the sum and the product. Letter E says, what complex number can you multiply 3 plus 2i by to get a real number? So again, if you looked at all these, the real number was the same, the imaginary part was opposite. Again, we learned that last week. Those are called complex conjugates. So the complex conjugate of this would be 3 minus 2i. So if I multiply 3 plus 2i times 3 minus 2i, I would get a real number. If you go to G, it says what complex number can you multiply a plus bi by to get a real number? So again, the real number stays the same. The imaginary part is opposite, so it'd be a minus bi. If we look at these two numbers, it'd be negative 4 plus 5i. It says multiply that, negative 4 plus 5i, negative 4 plus 3i. These are not conjugates, so let's see what happens when we multiply them together. We are going to have to FOIL. Negative 4 times negative 4 is 16. Negative 4 times 3i is negative 12i. 5i times negative 4 is negative 20i. And 5i plus 3i is 15i squared. And so when we do this, 16 minus 32i, and I get 15 times negative 1. So 15 times negative 1 is negative 15. 16 minus 15 is 1. I get 1 minus 32i. That is not a real number. That's a complex number still. So just because you're multiplying two complex numbers together does not mean you're going to get a real number. They have to be conjugates. The only way you can get a real number from complex numbers is if you're multiplying by a conjugate or adding by its conjugate. All right, we're going to remember this now as we go on to 84. 84 is where we're really reversing this process. So it says what equation has these solutions? We're going to look at 83's part A and B, where we're saying, all right, well, if these are my roots, what would my original equation look like? So if we look at 86, said Austin had an idea. He knew that if 3 and 5 were solutions of a quadratic equation, then x minus 3 and x plus 5 would be the factors that could be multiplied together to get a quadratic polynomial. Use his idea. How could his idea be used with the pairs of complex solutions in problem 83? Choose one pair and show how it works. So I'm going to use that pair for A of 2 plus I and 2 minus I. So we know 2 plus I and 2 minus I are solutions. So if we're writing those as factors, the factors would be, remember it's always x minus whatever your actual root is. So the factors would look like this: x minus 2 plus I, and then x minus 2 minus I. Okay, so again, I put the minus because the factor is always the opposite of what you see as the root or the solution. So before I start multiplying this out, I am going to distribute my negative sign through here. So I'd have x minus 2 minus I, and then I would have x minus 2 plus I. And so now you're doing a trinomial times a trinomial. You could just take, you could do this one a couple ways. You could take the x times all the three terms, the negative 2 times all three terms, the negative 1, the negative I times all three terms. I like to do the area model for that. So if you don't do the area model, that's fine, but whatever way you can multiply these is fine. So I'm going to write the x minus 2I on the top, and the x minus 2 plus I along the side, and then I multiply. So I get x times x is x squared, negative 2 times x is negative 2x, I times x is ix, x times negative 2 is negative 2x, negative 2 times negative 2 is positive 4, I times negative 2, I times negative 2 is negative 2i, and then I have negative I times x is negative ix, negative 2 times negative I is positive 2i, and then I have I times negative I is negative I squared. So now when I go ahead and I try to figure this out, I have x squared minus 4x plus 4, so that's what I had. Then I have minus ix, I have a positive ix here and a negative ix there, so those ix's cancel. I have a negative 2i here and a positive 2i there, so those cancel, and I have a negative I squared. And so as I clean that up, I would say x squared minus 4x plus 4 minus a negative 1, because I squared is negative 1. So I end up with the equation y equals x squared minus 4x plus 5. So what that means is that if I were to start with this equation and I solve this equation either completing the square or with the quadratic formula, my two answers would have been x equals 2 plus I and x equals 2 minus I. So again, it's just working backwards. So that's one way you can do it. Just take x minus the solution and distribute, or triple distribute, or do the area model. The other way is Melvin's way, and he said, why not just let x equals negative 4 plus or minus I and work backwards? So he's talking about this problem where our answers were negative 4 plus I and negative 4 minus I. And what we're going to do here is say, all right, we're going to really do like the reverse of completing the square. So here is x equals negative 4 plus or minus I, and if you think about the completing the square, you do the opposite operation. So I'm going to ultimately add the 4. You get x plus 4 equals plus or minus I. And then if you recall, the way we got that on completing the square is we took the square root of each side. So the opposite of square root is squaring. So I'm going to square each side. And so when I square a binomial, remember it's x plus 4 times x plus 4. And then plus or minus I squared, no matter whether it's positive or negative, it just becomes I squared. And then we have I'd have to FOIL this here. X times x is x squared plus 4x plus 4x plus 16. And we know I squared is negative 1. All right, I do want to get it y equals to get my equation, because it always has to be y equals. So that means I have to move this negative 1 to the other side. So my final equation is going to be x squared. I add my like terms here, 8x, 16, I added the 1 plus 17. So again, what that means is if I solve this via quadratic formula or completing the square, my solutions would be negative 4 plus or minus I. So again, those are your two ways. You can do x minus the factor and distribute, or you can set x equal to your solution and then just do the opposite steps of completing the square. I honestly think, for the most part, the Melvin way, the opposite of completing the square, is your easier way. But sometimes you are going to need to multiply it out depending on your problem. So that's why we're going to go both ways. The last part of the problem we're going to look at is problem 101. And for problem 101, it says, based on the following graphs, how many real roots does each polynomial have? So remember, real roots means it's actually crossing the x-axis. So if we look right here, it's crossing the x-axis here, crossing the x-axis there. So there are 2 real roots for this one. If we look at letter B, it's crossing right there, crossing here, crossing here. So that is 3 real roots. Graphs A and B above have been vertically shifted to create graphs C and D below. How many real roots does each polynomial function have now? So if we look, it's not crossing the axis at all now. So this would be 0 real roots. And now it's only crossing 1 time right here. So now this only has 1 real root. So it says the polynomials in part C and D do not have fewer roots. Polynomial C still has 2 roots, but now the roots are complex. So ultimately, if you can still draw like an x-axis through there somewhere, those are going to create complex roots. Polynomial in letter D still has 3 roots, but 2 are complex and 1 is real. So this has 1 real and your other 2 are complex. And this has just 2 complex. So really, anytime it's kind of shifting directions, that's really creating some roots. The one thing you also need to realize is that complex roots come in pairs. They're the conjugate pair, so that's why it's always like 2 plus or minus 5i, something like that. It's always plus or minus. Complex roots always come in pairs. So we'll write that down. Because they're going to be your conjugates. Okay, so you can never have just 1 complex root, or you can never have 3 complex roots, or 5. You can always have 2, 4, or 6, because you have to have the conjugates of each.